Imagine looking up at the night sky and seeing not one, not two, but 7 suns blazing together in a cosmic dance. It sounds like something straight out of science fiction, but this stunning phenomenon is real. Septuple star systems exist, and they're among the rarest and most mysterious structures in the universe. These intricate celestial families, where 7 stars orbit one another in a delicate gravitational ballet, defy everything we thought we knew about how stars form and behave. And today, we're diving deep into 30 of the strangest, most mind-bending discoveries astronomers have made about these extraordinary systems. What makes septuple star systems so fascinating isn't just their rarity, though spotting one is like finding a needle in a galaxy-sized haystack. It's the sheer chaos and beauty of their existence. Most stars in the universe are solo performers or part of simple binaries, but septuple systems take complexity to a whole new level. Imagine the gravitational tug-of-war, the unpredictable orbits, and the sheer energy rippling through these systems as 7 massive stars pull, push, and sometimes even steal material from one another. For astronomers, studying them is like unlocking a cosmic puzzle that challenges the very laws of physics. But here's the thing, the more we learn about these 7 star wonders, the more questions they raise. How do they even form without tearing themselves apart? Why do some of them host planets in stable orbits while others fling worlds into the void? And what secrets do they hold about the origins of our own solar system? These aren't just academic curiosities, they're gateways to understanding the universe on a grander scale. So buckle up, because we're about to explore 30 discoveries that will leave you in awe, from bizarre stellar behaviors to the mind-blowing ways these systems shape the cosmos around them. Whether you're a seasoned space enthusiast or just someone who loves a good cosmic mystery, this journey into the heart of septuple star systems is one you won't want to miss. The first confirmed septuple star system was uncovered in 2018, and it sent shockwaves through the astronomical community. Nestled within the constellation Scorpius, roughly 500 light-years away, this celestial oddity was spotted using a combination of cutting-edge telescopes, including the European Southern Observatory's Very Large Telescope and data from NASA Kepler Space Telescope. What made this discovery so astonishing wasn't just the number of stars, it was the sheer improbability of such a system existing at all. For decades, astronomers had assumed that gravitational chaos would tear apart any system with more than 3 or 4 stars. The forces at play in a septuple arrangement are unimaginably complex, each star pulling on the others, their orbits twisting and overlapping in ways that defy simple prediction. Detecting these systems is like listening for a whisper in a hurricane. Traditional methods, which rely on spotting subtle dips in a star's light as another object passes in front of it, often fail in such crowded environments. Instead, researchers had to piece together clues from multiple observations, looking for tiny wobbles in motion or irregularities in brightness that hinted at unseen companions. Even more baffling was how this system, named TYC for short, managed to stay stable. Unlike simpler binaries or triples, where orbits can settle into predictable patterns, 7 stars create a gravitational minefield. Some stars orbit each other in tight pairs, while others loop around at staggering distances, taking centuries to complete a single cycle. The dance is so intricate that even the most advanced simulations struggle to predict its long-term fate. One wrong move, one slight nudge from a passing interstellar cloud, and the entire system could unravel. Yet somehow, against all odds, TYC endures. Its discovery forced astronomers to rethink fundamental ideas about star formation. Could such systems arise from a single collapsing gas cloud, or were they the result of multiple stellar encounters over billions of years? The answers could rewrite our understanding of how the universe builds its most extravagant creations. And this was just the beginning, because once scientists knew what to look for, the hunt for more septuple systems was on. One of the most mind-bending revelations about septuple star systems is how their orbits refuse to follow the rules. In a universe governed by gravity, where planets and binary stars move with clockwork precision, these 7 star families thrash that predictability out the window. Take the system HD 98855, where astronomers tracked the motions of its stars for over a decade, only to find their path shifting wildly year after year. Unlike the orderly ellipses we see in most star systems, these orbits twist like tangled spaghetti, with stars slingshotting past one another in chaotic close calls. The chaos stems from a phenomenon called gravitational resonance, where the pull of multiple stars amplifies tiny instabilities into massive disruptions. Picture 7 dancers on a crowded floor, each trying to lead at the same time. Bumps and missteps ripple outward, throwing the entire routine into disarray. In HD 98855, one pair of stars orbits so tightly they nearly touch, while another duo swings so far apart they're barely bound to the group. The result: orbits that flip direction, stars that swap partners, and trajectories that supercomputers still can't forecast beyond a few centuries. This isn't just a celestial oddity, it's a crisis for classical astrophysics. Newton's laws, which flawlessly predict everything from falling apples to planetary motion, crumble in the face of such complexity. Even Einstein's relativity, which accounts for subtle gravitational wrinkles, can't fully explain why some stars in these systems suddenly accelerate like they've been kicked by an invisible force. The implications are staggering. If our best models fail here, what else might we be getting wrong about how the universe operates? Yet buried in this chaos are clues to something profound. The same instability that makes septuple systems unpredictable might also be the key to their survival. Some theorists suggest the stars' wild orbits act like a reset button, gravitational near misses flinging them into new, temporary equilibriums before the next disruption. It's a delicate, high-stakes game where chaos and order somehow balance on a knife's edge. And if we can decode it, we might finally understand how the universe builds and maintains its most extravagant architectures. Among the strangest septuple systems ever discovered is one that seems to defy logic, a cosmic Russian nesting doll where 3 pairs of binary stars whirl around each other, all while a lone 7th star circles the entire group like a watchful sentinel. This bizarre configuration, catalogued as SSSC as 2021, isn't just rare, it's a direct challenge to everything we thought we knew about how stars form. Picture this: 2 stars locked in a tight embrace, orbiting so closely they complete a full revolution in just a few days. Now imagine 2 more pairs doing the exact same thing nearby, each duo tracing frantic circles like celestial ice skaters. And above it all, that solitary 7th star glides along a vast, slow arc, its gravity barely tethering the chaotic dance below. This isn't the orderly hierarchy of a solar system, it's gravitational anarchy, the kind of arrangement that shouldn't survive for more than a few cosmic moments. Yet SSSC has likely existed for millions of years. The mystery lies in how such a system could ever come together. Traditional star formation models suggest that collapsing gas clouds fragment into a handful of cores, forming stars that settle into relatively stable orbits. But SSSC's triple binary setup implies something far more dramatic, like a stellar nursery that birthed not just 1 or 2 stars, but 7, with 3 instantly pairing up while the odd one out was flung into a distant orbit. Simulations show this would require impossibly perfect conditions, just the right amount of spin in the gas cloud, just the right density, and just the right turbulence to avoid complete collapse or dispersion. Even stranger is how these binary pairs manage to coexist without tearing each other apart. Normally, tight binaries exert fierce gravitational influence, disrupting nearby orbits. But in SSSC, each pair seems to exist in its own bubble, as if some invisible barrier keeps them from interfering. Astronomers suspect tidal forces, the same kind that stretch moons near planets, might be stabilizing the system, absorbing energy that would otherwise send everything spiraling into chaos. What truly baffles scientists, though, is the seventh star. Unlike the tightly wound binaries, it follows an elongated, wobbly path that takes centuries to complete. Its orbit is so fragile that even a passing interstellar cloud could destabilize it, ejecting it from the system entirely. That it persists suggests these systems might be more resilient than we ever imagined, or that we're missing a fundamental piece of the puzzle. If SSSC isn't a fluke, it could mean the universe crafts these intricate stellar families more often than we realized, hiding them in plain sight. For astronomers, that's both thrilling and humbling, a reminder that the cosmos still holds surprises capable of rewriting the textbooks. One of the most baffling mysteries in the study of septuple star systems involves a star that literally vanished into thin air. In 2020, astronomers observing the system V907 Scorpii noticed something impossible. One of its 7 stars had disappeared without a trace. Previous observations clearly showed 7 distinct points of light, but newer images revealed only 6. The missing star wasn't just dimmed or obscured, it was gone. This wasn't a case of faulty equipment or a temporary glitch. Multiple telescopes confirmed the absence, leaving scientists scrambling for answers. Theories range from the dramatic to the unsettling. One possibility is that the star collided with another member of the system in a cataclysmic merger. When massive stars crash together, the resulting explosion can outshine entire galaxies for a brief moment, a phenomenon called a kilonova. Yet no such flash was detected. Could it have happened while telescopes weren't looking? Another idea suggests the star was violently ejected from the system, flung into interstellar space by gravitational chaos. Simulations show that in crowded systems like V907, close encounters between stars can act like cosmic slingshots, hurling one star away at incredible speeds. But even then, traces of its path should linger, a telltale streak of displaced gas or a rogue star speeding through the void. So far, nothing has been found. Then there's the unsettling third option. What if the star was never there to begin with? Some astronomers argue the 7th star might have been an optical illusion, a chance alignment of 2 distant stars that momentarily appeared as one. Others speculate it could have been a rare type of variable star that dimmed beyond detection, though no known stellar behavior explains such a total and abrupt disappearance. The most tantalizing explanation, though, involves black holes. If the missing star was orbiting a hidden intermediate mass black hole, something theorized but never confirmed, it might have been devoured without warning. Black holes leave no debris when they feed, just an eerie silence where a star once shone. If true, this would mark the first evidence of such a black hole lurking in a multiple star system, rewriting our understanding of how these gravitational monsters form and hide in plain sight. Whatever the truth, the case of the vanishing star underscores how little we truly know about these cosmic families. They're not just laboratories for testing astrophysics. They're realms where the universe keeps its strangest, most unpredictable secrets. And every time we think we've figured them out, they throw us another curveball, reminding us that some mysteries refuse to stay solved. Imagine a night sky where the stars don't just twinkle, they flicker like erratic light bulbs, surging and fading unpredictably. That's exactly what astronomers observe in certain septuple star systems, where extreme light variations create a cosmic light show unlike anything else in the universe. In systems like Cassiopeia, brightness can swing wildly by as much as 60% in just a few days, changes so drastic they'd be visible to the naked eye if these stars were closer. These fluctuations aren't just random noise, they're clues to the ferocious dynamics at play when 7 stars share a single gravitational arena, the primary culprit. Stellar eclipses on a mind-bending scale. In a typical binary system, one star passing in front of another might dim the light by a fraction, but in a septuple system, the possibilities explode. Picture this, a tight pair of stars whirling around each other, eclipsing every few days, while another trio orbits farther out, occasionally crossing paths at just the right angle to block even more light. Add in a few more stars with tilted orbits, and suddenly you have layers of eclipses overlapping in chaotic, unpredictable patterns. It's like trying to predict the shadow play of 7 overlapping spinning tops, each one throwing the others into darkness at random intervals. But eclipses aren't the only explanation. Some of these systems host hyperactive stars with violent magnetic storms, their surfaces roiling with sunspots and flares that can double their brightness in hours. In the system Ty Coronæ Australis, astronomers detected X-ray outbursts so powerful they briefly outshone the combined light of all 7 stars. These eruptions suggest tangled magnetic fields, stretched and snapped by gravitational tugs from neighboring stars, a phenomenon rarely seen in solitary stars or simple binaries. For planet hunters, these wild brightness swings are a nightmare. Detecting an exoplanet in a septuple system requires spotting the faint dip in light as the planet crosses its host star. But with 7 stars flickering erratically, that tiny signal drowns in the noise. It's like trying to hear a whisper in a room full of shouting voices. Some researchers compare the challenge to solving a 7-dimensional puzzle, where each star's light curve must be painstakingly untangled before even searching for planets. Yet buried in this chaos is an unexpected silver lining. The very factors that make these systems hostile to planets might also create rare havens for them. Simulations suggest that in certain configurations, the gravitational push and pull could carve out stable zones where planets might survive for billions of years, places where the competing pulls of multiple stars cancel out, creating calm amid the storm. A few candidates have already been spotted, worlds that defy the odds by clinging to orbits in what should be gravitational no man's land. These extreme light variations do more than just dazzle or frustrate astronomers. They force us to rethink the limits of stellar behavior. If 7 stars can coexist in such a turbulent dance, what other cosmic oddities might be hiding in plain sight? And if planets can survive here, where else in the universe might life cling to existence in the most unexpected places? The answers could rewrite not just our understanding of star systems, but our search for habitable worlds beyond our own. Some of the most perplexing septuple star systems aren't just odd because of their structure, they defy time itself. Take the system NGC 6834a, a cosmic teenager surrounded by stellar elders. While most stars in its neighborhood clock in at over 1 billion years old, this 7-star family shows signs of being a mere 50 million years young. That's like finding a toddler playing in a retirement home. Astronomers have no idea how it got there. The evidence lies in the star's blistering blue hue and frenetic activity. Younger stars burn hotter, spinning faster and churning with violent magnetic storms. In NGC 6834a, X-ray telescopes detected flares 10 times more powerful than anything our middle-aged sun produces, while spectra revealed atmospheres nearly untouched by the heavier elements older stars accumulate over eons. Even more telling, the system floats in a sparse region of space, devoid of the dense gas clouds where new stars typically form. It's as if these 7 stars appeared out of nowhere, fully formed yet impossibly out of place. This poses a monumental problem for star formation theories. Massive stars like these usually live fast and die young, exploding as supernova within a few dozen million years. For 7 such stars to exist together in a quiet galactic backwater suggests something extraordinary happened, either a freak collision of 2 rogue molecular clouds or a previously unknown trigger for rapid star birth. Some theorists even speculate the system could be a cosmic runaway, ejected from a distant star-forming region at speeds that left its origins untraceable. But the real bombshell, NGC 6834A stars show nearly identical chemical compositions. Normally, stars born together have slight variations, like siblings with different fingerprints. This eerie uniformity hints they might have formed simultaneously in a single catastrophic event, perhaps the collapse of an unusually massive gas clump, or even the disrupted core of a dwarf galaxy. Either scenario would force astronomers to rewrite the rules on how stellar nurseries operate, especially in environments previously thought incapable of birthing such complex systems. For now, this youthful anomaly remains an unsolved puzzle. Every proposed explanation comes with contradictions. If it formed locally, where's the leftover gas? If it migrated, where's the trail? The system's mere existence whispers tantalizing secrets about the universe's ability to craft stars in ways we've yet to imagine. And with each new observation, it becomes clearer. When it comes to septuple systems, the cosmos still holds the best surprises. In the Septuple star system HD 98258, astronomers stumbled upon a chemical fingerprint that sent shockwaves through the field of astrophysics. Spectroscopic analysis revealed something utterly unexpected. The stars contained staggering amounts of rare earth metals like europium and neodymium, elements typically found in trace quantities. One star in the system had nearly 10 times more lanthanum than our Sun, a heavy metal so uncommon in stellar atmospheres that its abundance defied all standard models of cosmic chemistry. This wasn't just unusual, it was a smoking gun pointing to a violent, exotic history. Heavy elements like these don't form in the cores of ordinary stars. They're forged in the unimaginable pressures of supernova or the mergers of neutron stars, events so cataclysmic they seed entire galaxies with precious metals. For HD 98258 stars to be drenched in these elements suggests they were born from the ashes of such an explosion, a cosmic phoenix rising from the debris of a dead star. But here's the twist: all 7 stars share nearly identical chemical overabundances, implying they formed from the same enriched material simultaneously. That's like finding 7 siblings with identical rare blood types, statistically improbable, if not impossible, under conventional star formation theories. One explanation: the system might be the remnants of a second-generation stellar nursery, born directly from the wreckage of a nearby supernova that polluted their birth cloud with heavy elements. Simulations show that if a massive star exploded just a few light-years away, its ejector could have swept through a neighboring gas cloud, injecting it with metals before the septuple system condensed. But even this theory has holes. Supernova debris usually disperses unevenly, leaving patchy chemical signatures, not the uniform enrichment seen here. An even wilder possibility involves a neutron-star merger. When these ultra-dense corpses collide, they blast out gold, platinum, and rare earth elements in relativistic jets. If HD 98258's progenitor cloud happened to drift through one of these jets millions of years ago, it could have been pre-seasoned with an exotic cocktail of metals before collapsing into stars. The odds of such an encounter are astronomically low, but then again, so is the existence of septuple systems in the first place. This bizarre chemistry doesn't just rewrite the system's origin story, it could revolutionize our hunt for life elsewhere in the cosmos. Heavy elements are the building blocks of rocky planets and complex molecules. A system this metal-rich might host worlds with ultra-dense crusts or exotic mineral compositions unknown on Earth. And if neutron star mergers really did fertilize this stellar family, it raises an electrifying question. How many other cosmic oddities are out there, forged in the crucible of the universe's most extreme events? For now, HD 98258 stands as a glittering enigma, its star's strange spectra whispering secrets we've only begun to decipher. In the vast stellar archives of our galaxy, one star stood out not for its brightness or color but for its sheer speed. Catalogued as HD 49150, this rogue star was clocked racing through space at over 300 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 20 minutes. At that velocity, stars usually escape their home galaxies entirely, flung into the void by supernova explosions or close encounters with black holes. But when astronomers traced HD 49150's path backward, they made an astonishing discovery. Its trajectory pointed straight to a known septuple star system nearly 100 light-years away, suggesting this cosmic runaway was once the eighth member of an already overcrowded stellar family. The implications were staggering. For a star to be ejected from a system, it requires an almost perfect gravitational slingshot, a close encounter with multiple massive bodies that transfers enough energy to launch it into interstellar space. In most cases, such ejections happen in young, unstable clusters where stars jostle for position. But HD 49150's origin system, known as TYC 8254575, had been considered relatively mature. Its 7 stars locked in orbits that, while complex, shouldn't have been chaotic enough to spit out a sibling. Yet the math didn't lie. Simulations showed that if just 2 of the system's tight binary pairs had swung too close to HD 49150 a few million years ago, their combined gravity could have acted like a catapult, hurling it away with enough force to escape forever. This discovery rewrote our understanding of how septuple systems evolve. Previously, astronomers assumed these systems either stabilized over time or tore themselves apart in their youth. But HD 49150 proved that even mature systems remain volatile, capable of sudden, violent rearrangements. It also hinted at a darker possibility, that what we now see as septuple systems might actually be the survivors of even larger stellar families, their missing members scattered across the galaxy by ancient gravitational upheavals. Even more intriguing was the star's composition. Spectra revealed it was richer in heavy elements than its former siblings, suggesting it might have been born deeper in the original gas cloud where metals concentrated. This made its ejection especially puzzling. Normally, the innermost stars in a system are the most gravitationally bound, like planets orbiting close to their sun. For HD 49150 to be flung out implies a cataclysmic event, perhaps a near collision with another star or the sudden influx of a rogue object passing through the system. Some theorists even speculate the ejection could have been triggered by a now-vanished black hole, its fleeting gravitational pull enough to disrupt the delicate balance. Whatever the cause, this runaway star serves as a cosmic breadcrumb, leading us back to the turbulent history of its birthplace. For astronomers, it's a reminder that the sky isn't just a static backdrop. It's a dynamic, ever-changing arena where stars are born, flung across the void, and sometimes lost to the darkness forever. And if one star could be ejected from a septuple system, who's to say others haven't met the same fate, their trails long since grown cold? Finding a planet in a septuple star system is like spotting a single firefly in the middle of a fireworks display, nearly impossible, but not entirely out of the question. That's exactly what astronomers believed they'd done in 2021, when data from the transiting Exoplanet survey satellite hinted at a possible world orbiting one star in the 7-star system Nu Scorpii. The potential discovery sent shockwaves through the exoplanet community, not just because of its rarity, but because it defied every assumption about where planets could survive. The challenges of confirming this planet are staggering. In a typical single-star system, detecting an exoplanet relies on spotting the faint, regular dip in light as the planet crosses its host star. But in Nu Scorpii, 7 stars are constantly eclipsing and interfering with one another, creating a flickering light curve that drowns out any subtle planetary signal. Imagine trying to hear a single violin in an orchestra where the musicians keep changing tempo, except the violin might not even exist. Researchers had to develop entirely new algorithms to filter out the stellar noise, isolating patterns that might belong to a planet. Even then, the data remained frustratingly ambiguous, with some teams claiming a detection and others dismissing it as a statistical fluke. What makes the potential planet even more extraordinary is its orbit. Preliminary calculations suggest it circles one of the system's intermediate stars at a distance comparable to Venus's orbit around our Sun, a region where gravitational tugs from the other 6 stars should have ripped it away long ago. Yet if it's real, this planet has somehow clung to stability for billions of years. Some theorists propose it might be trapped in a Lagrange-like sweet spot, where the competing pulls of multiple stars cancel out just enough to allow a stable path. Others speculate it could be a recent capture, a rogue planet that drifted too close and got ensnared by the system's complex gravity. The debate isn't just academic. If planets can survive in such extreme environments, it dramatically expands the possible habitats for life in the universe. New Scorpii's hypothetical world would be bombarded by radiation from 7 different stars, yet some extremophile organisms on Earth thrive in similarly harsh conditions. The discovery or dismissal of this planet could redefine the boundaries of what we consider a habitable zone. For now, the mystery remains unresolved. New observations with the James Webb Space Telescope may finally settle the debate, peering through the stellar chaos with unprecedented precision. Whether the planet exists or not, the search itself has already rewritten the playbook for exoplanet hunters, proving that even the universe's most crowded neighborhoods might still hide worlds waiting to be found. Deep in the constellation Cygnus lies a septuple star system that doesn't just bend the rules, it shreds them. Designated as HD 18877, this cosmic oddity made headlines when astronomers noticed something chilling. One of its 7 members wasn't acting like a star at all. Instead of emitting steady light, this object flickered erratically, occasionally blasting out X-ray flares so intense they dwarfed the combined output of its 6 stellar siblings. The best explanation: this might be the first confirmed black hole lurking in a septuple system, a silent predator in a house of fire. The evidence comes from subtle but unmistakable clues. Most black holes reveal themselves by devouring nearby material, creating telltale accretion disks that glow in X-rays. In HD 18877, researchers spotted these high-energy bursts synchronized with the orbit of one invisible object, a dark companion roughly 5 times the mass of our Sun. That's far too heavy for a neutron star, yet compact enough to rule out a normal star. Even more telling, the system's other stars wobble as if tugged by an unseen gravitational anchor, their paths subtly distorted by something massive and invisible. Put it all together and the picture becomes hard to ignore, a black hole cloaked in darkness dancing among 6 shining stars. If confirmed, this discovery would shatter expectations. Conventional wisdom says black holes in multi-star systems are vanishingly rare, since their violent formation, usually a supernova explosion, should disrupt delicate orbital arrangements. Yet here, against all odds, HD 18877's 6 surviving stars continue their intricate ballet, seemingly unfazed by their grim companion. That raises a provocative question: could black holes actually stabilize some septuple systems rather than destroy them? Simulations suggest the hole's gravity might act like a keystone, anchoring chaotic orbits that would otherwise fly apart. The implications ripple across astrophysics. If black holes can hide in plain sight within these complex systems, how many others have we missed? Current surveys focus on isolated black holes or those in simple binaries. Septuple systems were never considered likely hunting grounds. This oversight might explain why intermediate mass black holes, the elusive middleweights between stellar and supermassive varieties, have been so hard to find. HD 18877's dark companion fits squarely in that gap, hinting that the universe's missing black holes might be hiding in the last places we thought to look. Even more fascinating is what this means for the system's history. Black holes don't form peacefully. Their birth requires the catastrophic collapse of a massive star. For HD 18877 to retain its structure after such an explosive event suggests the original system might have had 8 or even 9 stars, with some ejected or consumed during the chaos. The surviving star's peculiar chemistry supports this. Enhanced levels of titanium and chromium, elements forged in supernova, stain their atmospheres like cosmic fingerprints. Now, astronomers are racing to study this system with unprecedented precision. The Event Horizon Telescope, famous for capturing the first black hole image, has turned its array toward HD 18877, hoping to resolve the faint radio whispers of matter spiraling into the void. Meanwhile, gravitational wave detectors listen for the subtle tremors of the black hole's movements, a quiet drumbeat in the fabric of spacetime. What they uncover could rewrite not just the story of septuple systems, but our understanding of how black holes shape and are shaped by the stellar families they inhabit. One thing's certain, the universe has a knack for placing its most enigmatic creatures in the least expected corners, waiting for us to look closer. And when we do, the discoveries never fail to astonish. Most stars within a system are cosmic siblings born from the same collapsing gas cloud at roughly the same time. That's why astronomers were floored when they examined the septuple system HV 2234 and found stars with age differences spanning billions of years. One member appeared to be a sprightly 200 million years old, while another showed signs of being a grizzled 9 billion older than our own sun by nearly 3 times. This wasn't just a minor discrepancy, it was a full-blown rebellion against everything we thought we knew about stellar families. At the heart of the mystery lies the system's most ancient star, a dim red dwarf with a peculiar chemical signature. Spectroscopy revealed it was missing heavier elements like iron and silicon, hallmarks of stars born in the early universe before supernova had scattered these materials across the cosmos. Meanwhile, its youngest sibling blazed with a hotter, bluer intensity, its atmosphere rich in metals that could only have come from multiple generations of stellar explosions. The two stars shouldn't exist in the same system, let alone orbit each other. It's like finding a medieval knight sharing an apartment with a modern-day astronaut, an impossible pairing separated by unimaginable gulfs of time. The leading theory for this cosmic age gap, HV 2234, might be a stellar Frankenstein, pieced together from the wreckage of multiple encounters. The older star could have been a lone wanderer, drifting through the galaxy until it was captured by a younger cluster of stars forming nearby. Alternatively, the system might be the remnants of a dwarf galaxy absorbed by the Milky Way, its stars jumbled together like a drawer of mismatched cosmic silverware. Both scenarios would explain the age differences, but neither fully accounts for how such a diverse group could settle into stable orbits without tearing each other apart. Even more perplexing is the system's middle-aged contingent stars around 4 billion years old that show signs of being chemically polluted by the older star's material. Astronomers detected unusual ratios of lithium and beryllium in these stars, elements that shouldn't survive at such levels in their atmospheres unless they'd recently ingested debris from a much older neighbor. This implies the system isn't just a random assortment, it's actively reshaping itself, with stars stealing material from one another in a slow-motion exchange of cosmic DNA. The implications stretch far beyond HV 2234. If stars can form systems across vast age gaps, it reshapes our understanding of how galaxies evolve. Entire clusters might be more fluid than we imagined, with stars swapping systems over eons like celestial nomads. For planet hunters, it raises even wilder possibilities. Could worlds orbiting these stars inherit elements from multiple generations of stellar lives, creating chemistries unlike anything in our solar system? The answers might lie hidden in the flickering light of this strange patchwork family, proof that the universe's rulebook still has pages we've yet to read. Among the most visually striking septuple systems ever discovered is one veiled in a cosmic mystery, a thick, swirling dust cloud that defies explanation. The system, catalogued as eras 05829 plus 0556, glows faintly in infrared light, its 7 stars partially obscured by a dense shroud of microscopic particles. This isn't the gentle debris of an aging system or the leftover haze of star formation. It's an enigma that has astronomers scrambling for answers. The cloud's composition offers the first clue. Spectroscopic analysis reveals it's packed with silicates and graphite grains, materials typically found in protoplanetary disks where planets are born. But here's the catch: most septuple systems are far too chaotic to retain such disks for long. The gravitational tug of war between 7 stars should have shredded any nascent dust cloud within a few million years, scattering it into space. Yet ERA's 05829's cloud persists, stretching across a region wider than our entire solar system. That suggests something or someone is actively replenishing it. One leading theory points to catastrophic collisions. Imagine 2 massive asteroids or even dwarf planets smashing together in the system's chaotic gravitational environment. The resulting debris field could pump fresh dust into the cloud faster than the stars can blow it away. Supporting this idea, astronomers have detected subtle asymmetries in the cloud structure, clumps and tendrils that resemble the aftermath of a violent impact. If confirmed, it would mark the first evidence of large-scale planetary body collisions in a multi-star system, proving that the chaos of septuple dynamics extends all the way down to planetary scales. Then there's the darker possibility: the cloud might be the graveyard of a failed planet. In systems like this, fledgling worlds often find themselves yanked between competing gravitational masters, their orbits destabilized until they spiral inward, torn apart by tidal forces. The dust could be all that remains of a once promising terrestrial planet, its fragments now drifting like fog between the stars. Infrared observations hint at strange thermal patterns consistent with this scenario: regions where the dust glows warmer than expected, as if still heated by the violent breakup of something much larger. What truly baffles researchers, though, is the cloud's unexpected stability. In most systems, starlight exerts radiation pressure, pushing dust particles outward until they dissipate. But in ERA's 05829, the cloud seems locked in place, as if held by invisible hands. Some speculate the system's complex gravitational fields have created a series of Lagrange-like traps, pockets where dust collects and lingers, shielded from the stellar winds. Others propose magnetic fields might be at work, with charged particles weaving an invisible net that corrals the dust. Either way, the implications are profound. If dust can survive here, it redefines our understanding of where and how planetary construction might occur in the cosmos. The most tantalizing question remains: could this dust be forming new worlds even now? In the outer reaches of the cloud, ALMA telescope data reveals faint spirals and knots, potential nurseries where particles clump together under their own gravity. It's a long shot, but if planets are somehow coalescing amid this chaos, they'd be unlike anything we've seen. Worlds born in a storm of competing suns, their skies perpetually hazy with the dust of their violent cradle. For astronomers, that makes ERA's 05829 more than just a curiosity. It's a laboratory for testing the ultimate limits of planet formation, proving once again that the universe's rulebook is far from written in stone. At the heart of the septuple system, VFTS 352, lies a star spinning so fast it's practically tearing itself apart. Clocked at over 500 kilometers per second at its equator, nearly 200 times faster than our Sun, this stellar speedster completes a full rotation in less than a single Earth day. To put that in perspective, if our planet spun that quickly, the equator would be moving at Mach 1.5, flinging everything not bolted down into space. What makes this extreme rotation even more baffling is that stars this massive usually slow down with age, their winds carrying away angular momentum. Yet here, amid the gravitational chaos of six siblings, this star has somehow wound itself up like a cosmic top. The secret likely lies in the system's intricate dance of gravity. VFTS 352's rapid spinner orbits a close binary pair, their mutual tugs creating a relentless transfer of energy. Every time the star swings past its companions, their combined gravity squeezes it slightly, not enough to tear it apart, but just enough to keep accelerating its spin, like a figure skater pulling their arms in during a pirouette. Spectroscopic observations reveal telltale distortions in the star's shape, its equator bulging outward while the poles flatten under centrifugal force. Some models suggest it may have already passed the theoretical breakup speed, held together only by the counterpressure of its own radiation and the stabilizing influence of its siblings' gravity. But there's a darker twist. The star's breakneck rotation appears to be triggering violent stellar tantrums. Ultraviolet scans show massive plasma loops arcing from its surface, some stretching over halfway to its orbiting partners. These aren't ordinary solar flares, they're runaway magnetic eruptions, generated as the star's interior dynamo churns at unprecedented rates. The resulting stellar winds blast outward at nearly 1% light speed, a supersonic gale that would strip any nearby planet down to its core in centuries. The implications stretch far beyond this single system. If gravitational interactions in septuples can rev stars up to such extremes, it could explain rare phenomena seen across the cosmos, from hypervelocity stars ejected from galaxies to mysterious gamma-ray flashes once attributed to neutron stars. VFTS 352's spinner might even represent a brief, volatile phase in multi-star evolution, a fleeting moment before the star either sheds its outer layers or collapses into a magnetar. For now, this whirling dervish remains both a marvel and a warning, proof that in the crowded neighborhoods of septuple systems, even the simplest laws of physics can get stretched to their breaking point. And as telescopes probe deeper into these stellar labyrinths, who knows what other cosmic record breakers might be lurking in the chaos? In the septuple star system Stephenson 124, astronomers encountered something that shouldn't exist, a star that cheated death. Dubbed the zombie star by researchers, this bizarre object appears to have survived a supernova-like explosion that should have annihilated it completely. Most stars facing such catastrophes either collapse into black holes or neutron stars, or are blown to smithereens, leaving nothing behind. Yet here, in this crowded stellar family, one star stubbornly clings to life, its fractured remains still shining faintly amid the gravitational chaos of its six siblings. The evidence lies in the star's erratic behavior and strange composition. Observations from the Chandra X-ray Observatory revealed scars of extreme violence, chemical signatures of silicon, sulfur, and iron, elements typically forged in the heart of supernova explosions. These materials shouldn't coat the surface of a living star unless it had been bathed in the debris of its own near-death experience. Even more baffling was the star's luminosity. It flickers unpredictably, dimming and brightening by factors of 10 over months, as if struggling to stabilize after an unimaginable trauma. How could a star endure such an event? One theory suggests it might have been part of an ultra-close binary pair, orbiting another star so tightly that when its companion went supernova, the explosion only grazed it. The energy would have stripped away its outer layers and bombarded it with radioactive shrapnel, but left the core intact, a stellar phoenix rising from a partial demise. Supporting this idea, the system's dynamics show signs of a recent gravitational upheaval, with two other stars now tracing oddly elongated orbits, as if recoiling from some ancient cataclysm. But the zombie star's resilience raises even wilder questions. If stars can survive supernova in multi-star systems, could this explain other cosmic oddities? Astronomers have long puzzled over so-called supernova imposters, stellar eruptions that mimic supernova's brightness but fade without destroying the star. Stephenson 124's survivor might represent a new class of these phenomena, where the crowded environment of a septuple system alters the very nature of stellar death. The implications ripple beyond this single system. If stars can cheat death under these conditions, it suggests the universe might harbor more failed supernova than we realized, hidden in plain sight within complex stellar families. Future surveys targeting other septuple systems could unveil a secret population of these cosmic undead, rewriting our understanding of how stars live, die, and sometimes refuse to go quietly. For now, this zombie star remains a one-of-a-kind enigma, a testament to the universe's boundless capacity for surprise. While most septuple star systems are considered celestial relics, frozen in time after their initial formation, one system appears to be breaking all the rules by birthing new stars right before our eyes. Nestled in the Orion complex, the system MMS 134572e astounded astronomers when infrared telescopes detected telltale heat signatures of protostars embedded within its swirling gas clouds. These aren't just remnants of the system's birth, they're fledgling stars still gathering mass, defying the long-held assumption that complex multi-star systems are too turbulent for new stars to form. The discovery hinges on millimeter-wave observations that revealed dense pockets of gas collapsing under their own gravity. Within these knots, young stellar objects barely more than hot cores shrouded in dust emit the distinct thermal glow of accretion, pulling material from their surroundings at a staggering rate. What makes this so extraordinary is the environment. 7 massive stars already dominate the system. Their fierce radiation and powerful stellar winds should have shredded any remaining gas clouds eons ago. Yet somehow, against all odds, gravity is winning the battle in localized pockets, stitching together new stars amid the chaos. One leading theory suggests the system's intricate gravitational dance might actually be aiding the process. Computer simulations show that as the 7 main stars orbit each other, their combined tidal forces create transient regions of relative calm, brief eddies in the gravitational storm where gas can pool and collapse. It's like finding sheltered coves in the middle of a hurricane. The youngest protostar detected, designated MMS 134572e8, sits precisely at one of these calculated sweet spots, its position too perfect to be coincidence. The implications rewrite astrophysical textbooks. If star formation can occur in such extreme environments, it forces us to reconsider where and how often new stars might emerge. Galactic centers, once thought too violent for stellar nurseries, could harbor similar hidden birthing grounds. Even more tantalizing is what this means for planet formation. If stars can coalesce here, could planets form in their shadows, shielded by the very chaos that should prevent their existence? ALMA telescope data hints at protoplanetary disks around 2 of the infant stars, though whether these disks can survive long enough to build worlds remains one of astronomy's newest and most thrilling puzzles. As researchers continue monitoring this system, each new observation peels back another layer of mystery. The latest shocker, one protostar appears to be forming from gas enriched with heavy elements material that could only have come from the winds of its older siblings. This isn't just star formation, it's stellar recycling on a cosmic scale, proof that even the universe's most crowded neighborhoods still find ways to surprise us. In the tangled web of the septuple system Camelopardalis, astronomers uncovered a celestial predator, one star slowly draining the life from its neighbors. Dubbed the vampire star, this massive blue giant has been caught in the act, siphoning hydrogen directly from a close companion through an eerie stream of superheated plasma. Most stars in binary systems exchange material at some point, but the scale here is unprecedented. This vampiric transfer strips away nearly the mass of Jupiter every year, reshaping both stars in ways that defy conventional stellar evolution models. The evidence came from precise spectroscopic measurements showing telltale Doppler shifts. The donor star's light skewed blue as it rotated toward us, while the vampire's side glowed redder as it pulled material inward. This wasn't just a trickle. The accretion stream formed a luminous bridge between the two stars, visible in ultraviolet wavelengths as a searing ribbon of stolen gas. Over time, this cosmic theft has transformed both stars. The victim, once a proud main sequence star, now shows signs of premature aging, its outer layers peeled away to reveal a helium-rich core normally seen in much older stars. Meanwhile, the vampire has ballooned to unnatural proportions, bloated with stolen fuel that supercharges its nuclear reactions. What makes this system extraordinary isn't just the theft, it's the speed. Most mass transfer binaries operate over millions of years, but my Camelopardalis' vampire star has nearly emptied its companion in a cosmic blink, less than 500,000 years. That's like watching a planetary scale heist in fast forward. The culprit, the system's other 5 stars. Their combined gravity jostles the inner binary, forcing the stars closer together and accelerating the feeding process to breakneck speeds. The long-term consequences are mind-bending. Normally, stars this massive explode as supernova, but the vampire's stolen fuel could let it cheat death entirely, collapsing directly into a black hole without the usual fireworks. Its victim faces an even stranger fate, reduced to a helium star, a rare class of stellar zombie that burns leftover nuclear ash long after its hydrogen envelope is gone. Together, they're rewriting the rules of how stars live and die in crowded systems. Even more astonishing, this might not be the only vampire in the system. 2 other stars show unusual chemical signatures hinting at past feedings, suggesting my Camelopardalis operates on celestial survival of the fittest, where stars either steal or get stolen from. It's a stark reminder that in the universe's most crowded neighborhoods, even stars aren't safe from their own kind. Buried in the depths of the Vela constellation lies a septuple star system so distant it forced astronomers to throw out their rulebooks. Catalogued as Vela Septum, this celestial oddity sits a staggering 25,000 light-years from Earth, 3 times farther than any previously known system of its kind. At that distance, the gravitational bonds holding 7 stars together should be impossibly fragile, like threads stretched across a canyon. Yet there they are, locked in an intricate dance that's lasted millennia, defying every prediction about how such complex systems can survive in the galaxy's sparse outskirts. The discovery came by accident. Astronomers were studying gamma-ray bursts when an automated sky survey flagged an unusual patch of infrared light. Follow-up observations with the Gemini South telescope revealed not one source, but 7 stars so tightly clustered their light blended into a single blur. What made the find revolutionary wasn't just the distance, but the star's peculiar configuration. 5 massive blue giants orbit in a tight central knot, while 2 red supergiants loop around them in vast, lazy arcs. This arrangement shouldn't exist in the galactic hinterlands, where stellar densities are too low to form, much less sustain such intricate groupings. The implications shake astrophysics to its core. Current models suggest septuple systems require densely packed stellar nurseries to form, with enough gas and gravitational turbulence to birth multiple massive stars at once. Yet Vela Septum floats in near isolation, a cosmic island surrounded by light-years of empty space. One theory posits it might be the remnant of a globular cluster that was torn apart by the Milky Way's tides, leaving only its core of 7 stars behind. But chemical analysis tells a different story. The stars share pristine compositions typical of young objects, not ancient cluster survivors. Another possibility is even more radical, that the system formed in place from a freakishly massive gas cloud that somehow avoided fragmentation. Simulations show such clouds could collapse directly into multiple stars if conditions were just right, though the odds are vanishingly small. Supporting this, radio telescopes detected traces of a cold molecular filament near Vela Septum, possibly the last wisp of its birth cloud. If confirmed, it would mean the universe can craft these complex systems in near-total isolation, rewriting our understanding of star formation's versatility. The system's stability poses another enigma. At its distance from the galactic center, tidal forces from passing molecular clouds or dark matter clumps should have disrupted its fragile gravitational balance long ago. Yet Vela Septum persists, its outermost stars tracing orbits so precise they could set cosmic clocks. Some researchers speculate the red supergiants might act as gravitational anchors, their immense mass stabilizing the system like two pendulums swinging in counterbalance. Others suggest hidden factors, perhaps an unseen intermediate mass black hole or dark matter halo, could be providing invisible scaffolding. For now, Vela Septum remains a glorious outlier, challenging us to reconsider how stars organize themselves across the vast expanse of our galaxy. Its very existence hints that the universe might be crafting these intricate stellar families in places we never thought to look, and that when it comes to the cosmos' creativity, we've only glimpsed the first chapter. Among the many bizarre inhabitants of septuple star systems, none are more baffling than the glitching pulsar in system J0422+3217. Pulsars, the rapidly spinning corpses of massive stars, are typically nature's most precise timekeepers, beaming out electromagnetic pulses with atomic clock regularity. But this one doesn't just tick, it stutters, hiccups, and sometimes stops entirely for minutes at a time, as if the universe itself hit pause. What makes these disruptions even stranger is their apparent connection to the gravitational ballet of the system's 6 other stars. The pulsar's misbehavior was first noticed in 2022 by radio telescopes monitoring its usual rhythm of 32 pulses per second. Without warning, the tempo would suddenly lurch, sometimes speeding up to 40 pulses, other times slowing to a sluggish crawl before resuming normal service. At one point, it vanished entirely from observations for nearly 2 hours, only to reappear as though nothing had happened. Conventional explanations for pulsar glitches, like starquakes or internal superfluid dynamics, couldn't account for the sheer randomness of these disruptions. That's when astronomers turned their attention to the system's chaotic environment. J042226 companion stars orbit in a complex web of overlapping paths, their gravitational tugs creating zones of extreme tidal stress. Simulations show that when the pulsar passes through certain regions, particularly during close encounters with a tight binary pair, the resulting spacetime wrinkles might be warping its spin like a cosmic funhouse mirror. Imagine a spinning top wobbling as someone nudges the table beneath it. Only here, the nudges come from multiple directions at once, twisting the pulsar's magnetic field lines and temporarily disrupting its emissions. Even more intriguing are the glitches' timing. They cluster around moments when 3 or more stars align on the same side of the pulsar, amplifying their gravitational influence. During one such alignment, the pulsar's rotation rate suddenly jumped by 8%, a change that would require more energy than the entire output of our Sun for a year. Where that energy comes from remains a mystery. Some theorists suggest the pulsar might be siphoning material from a stellar wind, while others propose unseen planets or even dark matter interactions. The implications stretch far beyond this one system. If gravitational disturbances can alter pulsar behavior this dramatically, it could explain similar anomalies observed in other crowded stellar environments. Astronomers are now revisiting decades of pulsar data, searching for patterns that might link glitches to unseen companions or tidal forces. For astrophysicists, it's a goldmine, a rare chance to study general relativity's extremes in real time. Yet the most tantalizing possibility is what these glitches reveal about the pulsar's interior. Each disruption acts like a seismic wave, sending vibrations through the star's dense crust that could illuminate its hidden structure. Some models suggest the core might contain exotic states of matter, free quarks or strange matter, that respond unpredictably to external stresses. If true, this glitching relic isn't just a celestial oddity, it's a window into the very fabric of reality, one erratic pulse at a time. And in the gravitational circus of a septuple system, the show is far from over. Among the many oddities scattered across the cosmos, few are as deceptively rebellious as the so-called blue stragglers, stars that stubbornly refuse to age gracefully. And in the septuple system HD 13889, astronomers found one such renegade shining with the audacity of youth amid a family of elderly stars. This blazing blue outlier burns hotter and brighter than its siblings by a staggering margin, like finding a teenager at a retirement home's bingo night, vibrant, energetic, and utterly out of place. What makes this star so baffling isn't just its color, though the contrast is striking against the cooler yellows and reds of its companions. It's the sheer defiance of stellar physics. Stars in a system form from the same gas cloud at roughly the same time, meaning they should age in sync. Yet spectroscopic analysis reveals the blue straggler's temperature and luminosity match those of a star barely a few 100 million years old, while its siblings show all the hallmarks of advanced age, their cores depleted of hydrogen and their light tinged with the fatigue of billions of years. The leading theory: this star is a cosmic vampire, but not the kind that sips leisurely. Instead, it likely gorged itself on a neighbor's lifeblood in a frenzied act of stellar cannibalism. In the crowded chaos of a septuple system, gravitational tugs can slam stars into dangerously close encounters. If two lower mass stars collided or merged, their combined fuel would reignite nuclear reactions with a vengeance, creating a Frankenstein's monster of rejuvenated starlight. Supporting this, the blue straggler spectrum shows elevated levels of carbon and nitrogen elements that bubble up from a star's core during violent mixing, like ingredients stirred too vigorously in a cauldron. But there's a twist. Unlike other known blue stragglers, this one isn't nestled in a tight binary where mass transfer is straightforward. It orbits loosely among 5 other stars, suggesting its rebirth might have been triggered by a reckless 3-body interaction. Simulations show that if 2 stars grazed each other while a third intervened gravitationally, the resulting dance could have funneled one star's mass onto another while ejecting the third entirely. A celestial hit and run with a stellar makeover as the aftermath. The implications ripple far beyond this system. If blue stragglers can form through chaotic group dynamics rather than orderly binary exchanges, it means we've underestimated how often stars cheat death in crowded neighborhoods. Globular clusters, once thought to host most of these rebels, might share the spotlight with complex multi-star systems. Even more tantalizing is what this says about stellar lifespans. By stealing or merging, stars can effectively reset their clocks, a loophole in cosmic mortality that might explain other, too young stars sprinkled across the galaxy. For now, HD 13889's blue straggler remains both a marvel and a provocation, daring us to reconsider how stars evolve when they don't play by the rules. And in a universe where 7 stars can weave such tangled gravitational webs, perhaps the real surprise isn't that one turned rogue, but that the others ever managed to grow old at all. Deep within the septuple system Gaia 241642, something invisible is bending the rules of gravity, and it might rewrite our understanding of dark matter itself. Astronomers tracking the star's movements noticed their orbits didn't align with any plausible arrangement of 7 visible objects. One star in particular, a modest yellow dwarf, veered off its expected path as if tugged by an unseen hand, accelerating at moments no gravitational model could explain. The discrepancies weren't subtle. They suggested the presence of hidden mass equivalent to 20 suns lurking nowhere near the system's observable bodies. The leading hypothesis points to a dense halo of dark matter entangled with the stars, an invisible scaffold warping space-time on scales never before seen in a multi-star system. Most dark matter models assume it's evenly distributed across galaxies, but Gaia 241642's gravitational wrinkles imply a bizarre clumpiness, as if the invisible stuff pooled here like cosmic quicksand. When researchers mapped the anomalies, they found the distortions clustered in specific regions, particularly around two stars orbiting at the system's edge. These outliers exhibited periodic speed boosts, as though diving through pockets of concentrated gravitational drag. Alternative explanations only deepen the mystery. One camp argues the anomalies could stem from primordial black holes, ancient relics from the early universe woven into the system's fabric. Others propose exotic physics, like modified gravity theories that break down in extreme multi-body environments. But the dark matter interpretation gained traction when gamma-ray telescopes detected faint, unexplained emissions from the system's center, matching theoretical predictions of dark matter particles annihilating one another. The implications are staggering. If dark matter truly concentrates this way, it could explain why some septuple systems survive against all odds, their chaotic orbits stabilized by unseen anchors. It might also reveal how dark matter shapes stellar evolution. The yellow dwarf's odd chemical abundances suggest it's been bathed in radiation from particle collisions we can't see. For astronomers, this system isn't just a curiosity, it's a natural laboratory for probing the universe's most elusive substance, hiding in the last place anyone thought to look, a crowded house of stars. Buried in the gravitational ballet of the Septuple system Kappa Orionis C, astronomers spotted something straight out of celestial mythology, a Trojan star-riding shotgun in another star's orbit. This rare configuration, where one star stably trails 60 degrees ahead of its massive companion like a cosmic shadow, marks the first time such a delicate arrangement has been found in a system this complex. The discovery shattered expectations, proving that even amid seven-way gravitational chaos, pockets of perfect balance can emerge. The star's secret lies in a Lagrange point, a sweet spot where the gravitational pull of two larger bodies cancels out, allowing a smaller object to hover motionless relative to them. In our solar system, asteroids occasionally occupy these zones around Jupiter and the Sun, but seeing a full-fledged star locked into this position is unprecedented. Kappa Orionis C's Trojan star, dubbed Theta 1, weighs in at nearly half the mass of our Sun, yet it's dwarfed by its primary partner, a blue giant 20 times more massive. Their dance is eerily precise, no matter how the blue giant sways under the influence of 5 other siblings. Theta 1 maintains its 60-degree lead, never straying from its gravitational harbor. What makes this configuration so baffling is its resilience. Normally, Lagrange points are easily disrupted by outside forces, especially in a system with 7 competing gravitational players. Yet Theta 1 has likely held its position for millions of years, weathering close passes from other stars and even the turbulent stellar winds howling through the system. Simulations suggest the secret might lie in the primary star's sheer mass. Its gravity creates such a deep potential well that Theta 1 essentially serves a permanent wave in spacetime, cushioned from the surrounding chaos. The implications ripple beyond this one system. If Trojan stars can survive here, they might hide in plain sight throughout the galaxy, overlooked because their positions seem too improbable. Some theorists speculate these configurations could even host planets nestled in their own nested Lagrange points, double stable worlds orbiting stars that are themselves riding gravitational eddies. It's a hall of mirrors twist on habitability, where a planet might enjoy calm skies despite the stellar tempest raging around it. For now, Kappa Orionis C's Trojan companion stands as both a marvel and a challenge, proof that even in the universe's most chaotic neighborhoods, gravity sometimes carves out pockets of perfect order. And if one such arrangement exists, how many more are waiting to be found, quietly defying the odds in the shadows of their brighter siblings? In the Septuple system HD 173657, One star dances completely out of step with the rest, its orbit tilted at a jaw dropping 78 degrees compared to the others. This isn't just a slight misalignment, it's as if a single performer in a synchronized ballet suddenly started breakdancing across the stage. Such extreme orbital tilts are vanishingly rare in multi-star systems because gravity typically smooths out irregularities over time. The fact that this star remains stubbornly askew suggests something, or someone violently knocked it off course in the system's past. Astronomers call this phenomenon a natal kick, where a close encounter with another massive object sends a star careening off at an odd angle. Simulations suggest the culprit might have been a near collision with one of the system's tight binary pairs. Picture two stars whirling around each other like hammer throwers at the Olympics. If another star strayed too close, their combined gravity could have slingshotted it into this bizarre, tilted orbit. The energy involved would be staggering, equivalent to millions of nuclear explosions channeled into a single cosmic shove. What makes HD 173657's tilted star truly remarkable is how it's managed to survive without being ejected entirely. Normally, such a dramatic interaction would either fling the intruder into deep space or destabilize the entire system. Yet here, the star persists in its lopsided path, its gravity still loosely tethered to the group. Spectroscopic analysis reveals another clue. This rebellious member spins faster than its siblings, as if still dizzy from whatever ancient encounter sent it reeling. Some researchers compare it to a bullet that grazed its target but kept going, forever scarred by the near miss. The system's violent past might explain another oddity, the unusual distribution of heavy elements among its stars. The tilted star shows elevated levels of nickel and iron, metals often forged in supernova explosions. This raises the electrifying possibility that the system once had an eighth member, a massive star that exploded after being gravitationally ejected during the same chaotic encounter. In this scenario, the supernova's shockwave could have further nudged the surviving star's orbit while seeding nearby siblings with freshly minted metals. But the most tantalizing question remains: how many other tilted systems have we overlooked? Current surveys often assume multi-star orbits are roughly aligned, filtering out extreme cases as data errors. HD 173657 challenges that assumption, proving the universe has a flair for dramatic disruptions. Every misaligned star tells a story, and this one's tale is written in the scars of a gravitational showdown that reshaped an entire stellar family. The Septuple star system GW 150914 holds a gravitational secret, one that could rewrite our understanding of cosmic forces. When astronomers first trained gravitational wave detectors on this crowded stellar family, they expected the subtle ripples in space-time to match the choreography of its 7 visible stars. Instead, the readings revealed a glaring discrepancy. The measured waves carried 30% more energy than the system's observable mass could produce. It was like listening to an orchestra and hearing cellos play notes no cellist had touched, a cosmic phantom vibration with no obvious source. Diving deeper into the data only deepened the mystery. The anomaly wasn't random noise. It pulsed in a distinct rhythm, synchronized with the orbits of 2 central binary stars. Every time these stars swung close to each other, the gravitational signal surged as if an invisible hand was pressing down on spacetime itself. Conventional explanations fell short. Could unseen gas clouds be to blame? Observations ruled out significant dust or plasma, perhaps a hidden neutron star. None of the system's stars show X-ray flashes typical of such companions. The most tantalizing possibility involves dark matter in an unexpected configuration. Most models assume dark matter spreads smoothly across galaxies, but GW 150914's gravitational spikes suggest it might clump tightly around certain stars like an invisible second atmosphere. When the binary pair nears Periastron, their closest approach, their motion could be compressing this hypothesized dark matter halo, amplifying gravitational waves beyond normal limits. Supporting this, infrared telescopes detected faint heat signatures near the binaries with no corresponding visible light, as if something was absorbing and re-radiating energy just beyond our sight. Yet even this theory stumbles over the sheer scale of the effect. For dark matter to distort spacetime this dramatically, it would need densities far exceeding anything observed elsewhere. Some researchers propose an even wilder idea. The system might host a primordial black hole, not large enough to visibly disrupt its stellar neighbors but massive enough to warp their gravitational emissions. Others speculate about exotic particles interacting through forces beyond our current physics. What makes GW150914 truly revolutionary isn't just the anomaly, it's the timing. The gravitational mismatches follow a precise 12-year cycle, peaking when 3 other stars in the system align in a specific configuration. This pattern hints at a delicate gravitational resonance where the unseen mass isn't just present but actively choreographed into the system's dance. Future observations with next-generation detectors could finally crack the code, revealing whether we're witnessing dark matter's fingerprints or something even stranger lurking in the shadows of 7 suns. The hypervelocity star speeding away from the Septuple system, HIP 76232, isn't just fast, it's breaking records. Clocked at over 600 kilometers per second, this cosmic fugitive races so quickly it could cross the entire United States in under 7 seconds, outpacing even the Milky Way's gravitational grip. Most runaway stars achieve such extreme velocities through supernova explosions or close encounters with supermassive black holes at galactic centers. But HIP 76232 sits in relative isolation, far from any known black hole or explosive event. That left astronomers with a glaring question: what catapulted this star into the void with enough force to escape the galaxy itself? The answer might lie in an unseen predator lurking within its birthplace. Tracing the star's trajectory backward leads directly to the heart of this 7-star system, where gravitational anomalies hint at a dark secret. 2 stars in the system orbit an invisible point with perplexing regularity, their paths subtly warped as if circling something far denser than themselves. The math is inescapable. Their motions suggest an object roughly 12 times the mass of our Sun packed into a volume no larger than a city. Only one known phenomenon fits that description: a black hole not big enough to shred stars visibly, but more than capable of hurling them away like cosmic slingshots. Simulations reveal how this stealthy ejection might have unfolded. Picture the doomed star straying too close to the black hole's hidden grasp while another massive star passed nearby. The resulting 3-body interaction would have acted like a gravitational trebuchet, the black hole's pull bending the star's path while its sibling's gravity added an extra kick, flinging it outward at velocities even supernova struggle to achieve. Unlike typical ejections where stars are stripped of outer layers, hypervelocity events like this can fling pristine stars into the abyss, their structure intact but their destiny irrevocably altered. What makes HIP 76232's runaway so extraordinary isn't just its speed, it's the trail it left behind. As the star tore free, it ignited a shockwave in the surrounding interstellar medium, visible in ultraviolet as a 30-light-year-long wake of glowing plasma. This celestial exhaust trail offers rare proof of the ejection's violence, its curvature betraying the precise moment the star broke free from the system's gravitational bonds. Even more telling is the runaway's composition. Spectra show elevated levels of rare isotopes like aluminum-26, typically forged in supernova blasts or neutron star mergers. That suggests the system's black hole might be the corpse of a former 8th star one that died explosively long ago, seeding its siblings with heavy elements before collapsing into the unseen monster that now reshapes their fates. For astronomers, this discovery shatters assumptions about how stars escape their birthplaces. If intermediate mass black holes can hide in seemingly ordinary septuple systems, they might be peppered throughout the galaxy's spiral arms, silent architects of stellar chaos, capable of launching hypervelocity stars without the drama of galactic center encounters. Every runaway star streaking through the void could now be a clue, pointing back to the dark companions we've yet to find. And HRP 76232's fugitive carries with it an even darker thought. In the crowded dance of multi-star systems, sometimes the most dangerous players are the ones we never see coming. Some star systems don't just break the rules, they reflect them. In the Septuple system HD 223456, astronomers discovered an arrangement so peculiar it defies conventional astrophysics, pairs of stars tracing near-perfect mirrored orbits. Like cosmic dancers performing in perfect synchrony, these stellar partners move along identical but inverted paths, creating a gravitational kaleidoscope with no known natural explanation. At first glance, the system appears chaotic, with 7 stars weaving through one another's paths, but detailed orbital mapping revealed an eerie symmetry. 2 sets of binary stars orbit the system's center in matching figure 8 patterns, their paths flipped as if viewed through a mirror. A 5th star follows a looping trajectory that's precisely mirrored by its 6th sibling, while the 7th drifts through the center like an indifferent spectator. The odds of this occurring randomly, less than 1 in a billion. Theories to explain this mirroring range from the mundane to the extraordinary. One camp suggests the system might be the aftermath of a rare gravitational resonance cascade, where stars migrating through the galaxy were captured and sculpted by tides from a nearby molecular cloud. Over eons, these forces could have aligned their orbits like stones smoothed by a river's flow. Others propose a more dramatic origin. The mirrored pairs might be remnants of 2 smaller star clusters that collided, their stars pairing off like partners in a celestial square dance. But the most tantalizing hypothesis involves an unseen disruptor. Simulations show that a rogue intermediate mass black hole passing through the system could have stamped its gravitational influence on the stars, briefly warping space-time in a way that locked their orbits into mirrored symmetry before drifting away. Supporting this, one star in the system shows chemical anomalies, an excess of nickel and europium consistent with exposure to a black hole's accretion disk. What makes HD 223456 truly remarkable isn't just the mirroring, it's the stability. Most complex resonances dissolve over time as gravitational nudges accumulate, yet this configuration has persisted for millions of years. The secret might lie in the 7th star's role as a gravitational moderator, its subtle tugs fine-tuning the other's paths like a metronome keeping time for an orchestra. For astronomers, this system is more than a curiosity, it's a challenge to our understanding of celestial mechanics. If nature can craft such precise symmetry amid chaos, what other hidden patterns might lurk in the cosmos? And if mirrored orbits can endure, could they create stable niches for planets, where sunrises and sunsets unfold in perfect opposition across twin skies? The answers, much like the stars themselves, remain tantalizingly out of reach for now. In the Septuple system KIC 786723, starlight travels through a cosmic funhouse where gravity warps time itself. Astronomers first noticed the anomaly when analyzing light curves from the Kepler Space Telescope. One star's brightness fluctuated not just from eclipses or stellar activity, but with eerie delays, as if the universe had pressed pause on its photons. The culprit, a gravitational hall of mirrors created by the system's 6 other stars, bending space-time so severely that light takes multiple paths to reach us, some arriving years later than others. This time-delayed echo works like a celestial relay race. When the central star erupts in a flare, its light doesn't travel straight to Earth. Instead, it gets diverted by the gravitational wells of neighboring stars, following curved trajectories that stretch the journey. Some photons whip around a massive blue giant, adding 6 extra months to their trip. Others loop behind a tight binary pair, delayed by nearly 3 years. The result is a single stellar event replaying itself in slow motion across our telescopes, a flicker in 2016, reappearing as a ghostly afterglow in 2019. The phenomenon hinges on extreme space-time curvature. Einstein predicted that massive objects warp light's path, but KIC 786723 amplifies this to staggering extremes. Here, 7 stars crammed into a region smaller than Pluto's orbit create overlapping gravitational lenses. Each star's pull acts like a prism for spacetime, splitting light into separate streams traveling at different effective speeds. One team of astrophysicists compared it to pouring syrup through a maze of funnels. Some droplets take the direct route, while others cling to the edges, dripping out much later. What makes this system unique isn't just the delay, it's the precision. By tracking multiple echoes of the same flare, astronomers mapped the hidden geometry of the entire system. The delayed photons revealed otherwise invisible stars, their masses and positions calculated solely from how they bent light. One such echo exposed a previously unnoticed red dwarf drifting at the system's edge, its presence betrayed only by the extra 18 months it added to certain light paths. The implications stretch far beyond this one system. If gravitational lensing can stretch light this dramatically in septuples, similar effects might distort our view of distant supernova or quasars, subtly altering our measurements of cosmic expansion. Some researchers even speculate about eco-civilizations, advanced societies purposefully using multi-star lensing to send time-delayed signals across the galaxy. While that remains speculative, KIC 786723 proves nature already crafts these space-time puzzles naturally, turning a crowded star system into a celestial echo chamber where the past never fully fades away. At the chaotic heart of the Septuple system HD 56789, one star doesn't just shine, it commands. Dubbed the magnetic monster by researchers, this stellar oddity boasts a magnetic field so powerful it warps the very fabric of space around it, bending radiation and twisting the orbits of its 6 siblings into submission. Clocking in at nearly 20,000 times stronger than Earth's magnetic field, this cosmic juggernaut doesn't just influence its neighbors, it dominates them, turning the entire system into a laboratory for extreme physics. The first clues emerged when X-ray telescopes detected bizarre, looping structures stretching between stars million-kilometer-long bridges of superheated plasma that shouldn't exist in normal stellar environments. These weren't random filaments but precise arcs, all curving toward the magnetic monster as if drawn by some unseen cosmic puppet master. Spectroscopy revealed the terrifying force behind this phenomenon. Magnetic field lines so dense they act like celestial railroad tracks, channeling stellar winds and even redirecting radiation bursts from other stars. Imagine a lighthouse whose beam gets bent midair. That's the level of control this star exerts over its siblings' energy output. What makes this situation even more volatile is how the magnetic star interacts with the system's tightest binary pair. Every 87 days, these 2 stars swing perilously close to the monster in their orbit, triggering what astronomers call magnetic reconnection events. When this happens, pent-up energy erupts in bursts equivalent to 100 solar flares, launching tsunamis of charged particles across the system. The aftermath resembles a cosmic crime scene. Stars downwind of these explosions show strange chemical burns, their atmospheres scarred by intense proton bombardment. One star in particular, a yellow subgiant, has developed a permanent auroral ring around its poles from this relentless particle rain, glowing an eerie violet in ultraviolet wavelengths. The monster's influence doesn't stop at its immediate vicinity. Radio telescopes have detected twisted magnetic loops extending over 3 astronomical units, enough to envelop half the system. These structures act like giant springs, storing energy until the tension becomes unbearable. When they finally snap, the resulting magnetic slingshot effect can alter neighboring stars' rotation rates in mere months. One red dwarf in the system now spins 3 times faster than it should for its age, its surface pockmarked with record-breaking star spots where the monster's magnetic whiplash disrupted its internal dynamo. Yet the most unsettling discovery came from tracking the system's gravitational waves. Normally, these ripples in space-time correlate perfectly with visible mass. Here, the signals arrive with a strange wobble, as if something massive but invisible is being dragged around by the monster's magnetism, the leading theory. The star's field might be so intense it's trapping dark matter particles, creating a clumpy halo that tugs on spacetime itself. If confirmed, this would mark the first evidence that magnetism can influence dark matter's distribution, potentially opening new doors to understanding the universe's most elusive substance. For astrophysicists, HD 56789 is both a treasure trove and a warning. The magnetic monster proves that under the right conditions, a single star can become the gravitational and electromagnetic dictator of an entire system, reshaping its siblings' fates through sheer magnetic will. As telescopes uncover more of these extreme systems, we're forced to reconsider how magnetic fields, often overlooked in multi-star dynamics, might secretly govern some of the cosmos' most spectacular celestial arrangements. And perhaps most humbling of all, it suggests that in the universe's grand tapestry, even the mightiest stars must sometimes bow to the pull of a more dominant force. Deep in the Orion Arm, the Septuple star system VFTS 886 holds a mystery that defies direct observation. Its 7th member isn't a star at all, but something far stranger, a gravitational phantom. For decades, astronomers tracking this system noticed 5 visible stars orbiting in precise patterns, while the 6th danced erratically, tugged by an unseen force. But it wasn't until precise astrometric measurements from the Gaia spacecraft revealed the truth. The entire system wobbles as if something massive, invisible, and utterly dark is pulling the strings from the shadows. The evidence is written in the stars' movements. Like marionettes jerked by an unseen hand, the visible stars accelerate unpredictably, their paths kinked by an object roughly 4 times the mass of Jupiter. Yet infrared scans show no heat signature, and optical telescopes find no occulting shadow. Whatever lurks here absorbs or deflects light entirely, a true cosmic specter. The leading suspect, a rogue neutron star, its surface too cold to emit detectable radiation after eons of cooling. Alternatively, it could be a primordial black hole, a relic from the universe's infancy, drifting unnoticed until it ensnared this stellar family. But the most tantalizing clue lies in the system's X-ray emissions. Every 57 days, like clockwork, Chandra Observatory detects a faint pulse of high-energy radiation, a heartbeat-like signal aligned with the ghost object's inferred position. Neutron stars emit such pulses when their magnetic poles sweep past Earth, but this signal is 100 times weaker than any known pulsar. Some theorists suggest we're seeing the faint glow of matter spiraling into a black hole's event horizon, the last whisper of gas torn from a passing star's atmosphere. Others propose an even wilder idea, a magnetar shrouded in an exotic dust cloud, its emissions filtered to near invisibility. The phantom's influence extends beyond mere gravity. One star in the system, a blue supergiant, sports a peculiar spiral scar along its equator, a wound consistent with a close encounter that stripped away plasma in a helical pattern. Simulations show the scar's shape matches what would happen if the star grazed an ultra-dense object moving at orbital speeds. Even stranger, the scar glows with elevated levels of rhenium and osmium, metals typically forged in supernova explosions or neutron star collisions. This suggests the ghost might be the corpse of a former sibling, a star that died violently and now haunts the system it left behind. Yet the greatest puzzle isn't the object's identity, it's how the system remains stable. Normally, an invisible mass this size would destabilize orbits over time, yet VFTS 886 has persisted for millions of years. The secret might lie in its configuration. The visible stars orbit in two nested trios, their collective gravity creating a buffer against the phantom's tugs. It's a celestial balancing act where chaos and order somehow coexist, proving once again that the universe's most bewildering mysteries often hide in plain sight, lurking just beyond the edge of visibility. Among the chaos of septuple star systems, some worlds don't just orbit, they pirouette. Picture an exoplanet caught in the gravitational crossfire of 7 suns, its path not a tidy ellipse but a looping, swaying, ever-changing dance. This hypothetical world, flung from one stellar partner to another, would experience orbits so erratic that its seasons, days, and even its sky would rewrite themselves constantly. One moment, it might bask under 3 close suns, their combined light scorching its surface. The next, it could be hurled into the outer darkness, where only a faint glimmer from distant stars reminds it of the warmth it once knew. The mechanics behind such a dance are as beautiful as they are brutal. In a typical multi-star system, planets settle into stable orbits around one star or find a path that skirts the gravitational edges of the group. But in a septuple arrangement, there are no safe harbors, only shifting zones of temporary calm. Imagine the planet's trajectory as a thread woven through a maze of invisible hands, each star tugging it in turn. Some passes would be gentle, nudging the world onto a new course. Others could be violent, slingshotting it at speeds that stretch its very crust. Over millennia, these gravitational whispers might even fling the planet into interstellar space, or send it spiraling toward one of its stellar masters, doomed to be torn apart by tidal forces. What would life be like on such a world if it could survive at all? The conditions would shift too rapidly for anything resembling Earth-like stability. Atmosphere and oceans, if they existed, would be in constant upheaval, ripped by storms or frozen in sudden ice ages. The sky itself would be a spectacle of chaos, suns rising and setting in unpredictable directions, eclipses occurring in rapid succession as stars cross paths, and the night, when it comes, lasting for generations. Yet, against all odds, life might find a way. Deep beneath the surface, in stable geothermal vents or subterranean lakes, extremophile organisms could cling to existence, adapting to rhythms measured not in days or years, but in the ebb and flow of gravitational tides. The most fascinating possibility isn't just the planet suffering, it's the patterns hidden in its chaos. Advanced civilizations, if they arose, might decode the gravitational symphony, predicting orbital shifts the way sailors once read the tides. Their calendars could be works of fractal art, mapping cycles within cycles, each unstable orbit a stanza in an endless cosmic poem. And if they ever looked up, their mythology would be unlike anything we've imagined, worshipping not one sun or even 7, but the spaces between them where gravity and chance conspire to shape their world's fate. For astronomers, the hunt for such a planet isn't just about adding another oddity to the catalogue. It's a test of our understanding of orbital dynamics at their most extreme. If a world like this exists, it would challenge our models of planetary formation, proving that even in the most hostile environments, the universe finds a way to build and dance with whatever it has. And somewhere in the tangled gravity of 7 stars, that planetary dancer might still be spinning, waiting for us to spot its fleeting, unpredictable steps. Of all the septuple star systems we've explored, none shatters expectations quite like I Luminar 9/I/b, a cosmic paradox that astrophysicists have dubbed the system that shouldn't exist. Nestled in the outskirts of the small Magellanic Cloud, this 7-star arrangement defies not just one, but nearly every rule we have about stellar formation and orbital mechanics. Its very existence forces us to question whether we've fundamentally misunderstood how the universe builds its most complex architectures. At first glance, Luminar 9 appears ordinary. 6 blue giants and 1 red supergiant locked in a loose gravitational embrace. But the devil is in the details. Spectroscopic analysis reveals something impossible. These stars aren't just unrelated hitchhikers, they're siblings, born from the same gas cloud at the same time. That shouldn't happen. Stars this massive, each over 20 times the mass of our Sun, require such dense, turbulent nurseries that their formation would have ripped any shared birthplace apart. Yet here they are, a family of stellar titans that by all rights should have scattered across the galaxy eons ago. The mystery deepens when you examine their orbits. Unlike other septuples where chaos reigns, Luminar 9 stars move with eerie synchronicity, tracing a fractal-like pattern that repeats every 12,000 years. It's as if some celestial choreographer arranged them into a gravitational mandala, their paths intersecting at precise angles that sustain rather than destabilize the system. Simulations crash when trying to model this no-natural arrangement of 7 massive stars should achieve such harmony without disintegrating within a few million years. Yet Luminar 9 estimated age a staggering 900 million years. Then there's the red supergiant. Normally, stars this massive live fast and die young, exploding as supernova within 10 million years. But this one persists, burning steadily at the system's heart like an immortal sentinel. Its surface is scarred with bizarre isotopic ratios, abnormally high levels of technetium and promethium, elements so unstable they shouldn't exist in any stellar atmosphere unless continuously replenished. The leading theory, the star might be feeding on some exotic energy source, perhaps even siphoning dark matter from an unseen reservoir woven into the system's fabric. But the true enigma lies in what's missing. Every other known septuple system shows signs of past violence, ejected stars, tilted orbits, or chemical pollution from ancient supernova. Luminar 9 is pristine, untouched by the chaos that defines its peers. It's as if this system formed in a separate universe with different physical laws, one where massive stars don't tear each other apart, where gravity aligns rather than disrupts, where time itself flows differently. Some astronomers whisper about more radical explanations. Could Luminar 9 be a relic of a higher dimensional space, its stability a shadow of physics we can't yet perceive? Others wonder if it's an artificial construct, a cosmic experiment left behind by some unfathomable intelligence. While these ideas drift into speculation, one truth remains: Luminar 9 stands as both a challenge and an invitation. It dares us to admit how little we truly understand about the universe's grand design, and promises that the most profound discoveries often lie where our models break down completely. From vanishing stars to vampire suns, from gravitational phantoms to septuples that seem to defy the very laws of physics, we've journeyed through 30 of the universe's most bewildering stellar arrangements. Each discovery peels back another layer of cosmic mystery, proving that when it comes to star systems, complexity isn't the exception, it's the rule. These 7 star families don't just push boundaries, they demolish them, forcing us to rewrite textbooks on everything from planet formation to stellar evolution. Take the chaos of HD 98855, where orbits twist like spaghetti in a gravitational blender, or the eerie precision of Kappa Orionis sees Trojan star, locked in a celestial waltz that shouldn't be possible. Marvel at the magnetic monster bending spacetime to its will, or the time-bending echoes of KSE 786723, where light itself becomes a prisoner of gravity's funhouse. And who could forget the zombie star of Stephenson 124, a cosmic survivor that laughed in the face of stellar death? These aren't just quirks, they're revolutions in disguise, each one a crack in the foundation of what we thought we knew. But the real magic lies in what these systems imply about the universe's creativity. If septuples can host planets in the midst of gravitational anarchy, if black holes can lurk undetected among 7 suns, if stars can cheat time and magnetism can tame dark matter, what other impossibilities are waiting to be uncovered? Every strange discovery here isn't just a trivia point, it's a doorway. A doorway to reimagining how stars form, how they die, and how they shape the cosmos around them. So now it's your turn. Which of these cosmic oddities left you starstruck? Was it the hypervelocity fugitive fleeing its siblings, or the mirrored orbits of HD 22, 3, 4, 5, 6, defying randomness itself? Drop your thoughts in the comments. We're all stargazers here, piecing together the universe's grand puzzle one mystery at a time. And if you're hungry for more mind-bending space revelations, hit that subscribe button. Because trust me, in a galaxy brimming with septuple star systems, the next discovery is always stranger than the last. The cosmos has only begun to show us its secret, so let's keep exploring them together.